Welcome to the tutorial session. So, today we are going to look at some aspects of ADME. So, ADME is nothing but absorption, distribution, metabolism and excretion. So, we have been dealing with these concepts for the past few lectures, and so we will now look at some problems associated with these topics. Right. So, the first question is aspirin, which is acetyl salicylic acid, has a pKa of 3.5. Okay. So, the first subpart to this question is calculate the ratio of ionized by unionized of the drug in the stomach where the pH is 1. Okay. The second part is calculate the ratio of ionized by unionized in the intestine where the pH is 6, and based on these calculations, can you suggest where aspirin would be absorbed within the body? Okay. So, we are given these data. So, pKa of aspirin is 3.5, pH is 1 in stomach and pH in the intestine is 6. Right. So, what we need to find out is the log is the ionized divided by unionized. Okay. So, now in order to solve this problem, let us now look at the Henderson-Hasselbalch equation, which is basically pH of stomach to begin with equals pKa of aspirin plus log of ionized divided by unionized. Okay. So, this would be the first equation that we would want to write. Okay. So, in the case of salicylic acid, we have RCOOH and RCOO minus. Okay. So, the ionized form is RCOO minus and RCOOH is the unionized form. So, we have already discussed that the pH of the stomach is 1. So, this is equal to pKa of aspirin is 3.5 plus log of ionized divided by unionized. Okay. So, this is what we would need to find out. So, what we would do is we would then take 3.5 to the other side. So, log of ionized divided by unionized is 1 minus 3.5, which is equal to minus 2.5. Okay. So, in order to find this ratio over here, so we would need to take the antilog. So, the ratio of ionized by unionized would be antilog of minus 2.5, and this value turns out to be 0.00316. Okay. So, what this number means is that the ratio of RCOO minus divided by ratio of RCOOH is this number. Okay. So, for every 1000 unionized molecules, right, there are perhaps 3 ionized molecules. Okay. So, this being such a small number means that the molecule is predominantly in the unionized form. Now, let us look at the second part of the question, which is to find out the same ratio in the intestine. So, we have already been given pH of intestine equals pKa plus log of ionized divided by unionized, right. So, this is what we know from Henderson-Hasselbalch equation. So, again the numbers are pretty straightforward. This is 6 equals 3.5 plus this value, right. So, becomes 6 minus 3.5, which is 2.5. Okay. So, in order for us to look at this number, so this is basically log of ionized by unionized. Okay. So, if you take the inverse of this number, which will be basically log of unionized divided by ionized, you get a value of minus 2.5, which is exactly identical to what we got in the previous case. So, this value is concentration of unionized divided by ionized equals anti-log of minus 2.5, right, which is nothing but 0.00316, which is the same number that we got previously, except that the numbers, the numerator and denominator are actually flipped, right. So, here there is a larger concentration of ionized molecules. That means, RCOO minus is significantly greater than RCOOH. Okay. So, the next question, which is the third part of this question, is basically based on these calculations, where is aspirin absorbed within the body. So, if you look at the molecule, which is basically RCOOH and RCOO minus. So, this molecule is more lipophilic, right, and this is more hydrophilic. And so, what you would expect is that a more lipophilic molecule would get across the cell membrane better, and so this molecule should be in predominantly higher amounts. So, what we would predict is that since the majority of the molecule is in the unionized form in the stomach, the large amount of this molecule will be absorbed in the stomach and not in the intestine. The next question is, benzene used to be a very common solvent in the organic chemistry lab, but is no longer used because it is a suspected carcinogen, right. So, we have already looked at this previously, but benzene undergoes metabolic oxidation by P450 enzymes to form an electrophilic epoxide, which can alkylate proteins and DNA. Toluene, on the other hand, is a replacement that has been found, and toluene is also oxidized by cytochrome P450, but the metabolite is less toxic and rapidly excreted. So, the question is, suggest what the metabolite might be and why the metabolism of toluene is different from that of benzene. So, in order to address this or answer this question, first let us draw the structure of benzene, right, which is over here, and toluene, which is basically the benzene ring with a methyl group. Okay. So, benzene, as we mentioned here, is going to undergo epoxidation, and this can subsequently react with electrophiles. Okay. This is the reason why benzene is actually a potential carcinogen, but toluene on the other hand is not. So, one major difference between benzene and toluene is the presence of this methyl group. So, toluene can undergo oxidation to form CH2OH. This is catalyzed by CYP450, which can then subsequently be oxidized further to form the aldehyde, which can then again undergo oxidation to form the carboxylic acid. Okay. And we have already looked at the carboxylic acid can actually react with through conjugation reactions to give perhaps peptides for example, and this is going to be excreted. Okay. So, this itself is hydrophilic, and subsequently the carboxylic acid can undergo conjugation to give you more water soluble derivatives, which is then quickly excreted. So, therefore, toluene does not hang out in the body for as much time as benzene does, whereas benzene gets epoxidized, and we already looked at some of the deleterious effects of epoxides. So, the next question is, a drug has a half life of 4 hours. Okay. How much of the drug remains after 24 hours? So, in order to address this question, let us look at half life. Basically, half life is the time taken for the drug to drop by 50%. Okay. So, this can happen through any of the ADME processes. So, the absorption can occur, distribution of course is going to occur, metabolism and excretion. And so, what we are looking at is in the blood, right. Now, so the question here is, after 4 hours 50% remains. So, let us write them down, 4 hours 50%, which means that in another 8 hours 50% of this number would go down, which means that you would have, so 25% would still remain, okay. And in another 4 hours, which is 12 hours, you would again imagine, you could expect that another 50% of this 25% would be gone. So, you will have 12.5%, and in another 4 hours you will go to 16 hours, where this number would go down to 6.25%, which is exactly half of 12.5%, and in 20 hours it would further go down to 3.13%. Yeah. So, 24 hours it would go down to 1.56%. The next question is, atenolol's pKa is 9.6. So, the question is, predict whether it would be ionized in the stomach, right. So, in order to address this question, what we would need to do is to look at this structure very closely and see what are the functional groups which are going to be acidic or basic. So, when you are looking at bases, we have already seen that it is basically, it is the pKa of the protonated amine. So, between an amide and a secondary amine, the amine would be a better base. Okay. So, therefore, the pKa of this amine is expected to be 9.6 rather than the amide. Okay. Now, we have already seen that the pKa of alcohols is substantially higher, somewhere between 15 to 17, and so this would be this would not be the species that is going to get protonated or deprotonated. So, the question is whether this is going to be ionized in the stomach. So, we already looked at pH equals pKa plus log of ionized by unionized, right. So, since the pKa is 9.6, we would expect that a substantial portion of this molecule is going to be in the protonated state, because this number pH of 1 is much greater, is much more acidic, and therefore, it would be ionized in the stomach. The phenol group of morphine is important in binding to the opioid receptors, and this causes analgesia, right. Codeine, which has the same structure as morphine, but the phenol group is masked as a methyl ether. So, the phenol of morphine is actually masked as a OMe. As a result, codeine binds poorly to opioid receptors and should show no analgesic activity. However, when it is taken in vivo, it shows very useful analgesic properties. So, the question is, explain how this might occur. So, in order to address this question, so what we are looking at here is, this is morphine, the phenol of morphine, and this is codeine. And so, if you want to understand this point, we will have to look at how this molecule is actually going to be metabolized. So, let us draw the structure of codeine. So, this is the structure of codeine, OMe. Okay. So, here is the methyl group or methoxy group that we are talking about. So, what we would expect is that this methoxy group is going to be metabolized in the liver to produce the corresponding phenol, which is basically morphine, right. So, I am not drawing out the rest of the molecule, but you can imagine that this can occur in the liver, and therefore, codeine is actually demethylated and it is going to produce the active ingredient, which is morphine. The next question is, what would you expect as metabolites for methylphenidate? Okay. So, methylphenidate has the following structure. So, it has a piperazine ring, stereochemistry is over here going up, and it has a benzene ring, and it has a COOMe and a hydrogen. Okay. So, this is the structure of methylphenidate. Okay. So, by looking at this molecule, we can see that it has a number of functional groups that can be metabolized. Okay. So, we have already looked at the possibility of the phenyl ring getting oxidized. So, you could have oxidation over here. Okay. You can also have on the carbo cycle or the heterocycle, you have CH2s which are exposed, and these again can undergo oxidation. Okay. And we have already looked at that the nitrogen NH can undergo oxidation, and this ester can undergo hydrolysis. Okay. So, these are some of the important reactions of oxidation and hydrolysis, but in addition this NH can also undergo conjugation. Okay. So, we already looked at the possibility of conjugation with glucuronic acid with amines, and lastly it can also undergo methylation. Okay. So, these are the major reactions that we would expect with this molecule. So, to draw out some of the metabolites, let us draw the structure of this molecule once again. So, for example, if the ester is undergoing hydrolysis, you will end up with COOH, and the rest of the molecule remains the same. Okay. And if you think, if you suspect that the benzene ring is going to get oxidized, what might happen is that the benzene ring is going to form an epoxide, which can then do a hydride shift to give you a phenol, and we have already seen that the phenol formation is going to be favored in the para position when you have a substituent. So, this remains, the rest of the molecule remains the same. Okay. You could also have, as we discussed, oxidation at the nitrogen position. So, I am not going to draw out the rest of the molecule, but you could have N oxide being formed. We could also have methylation, which is shown over here. Right. And lastly, we can also have conjugation with other things which I am not, glucuronic acid, which I am not showing. But you can also have multiple things happening on the same molecule. So, for example, if this undergoes ester hydrolysis, then you would generate the phenol remains the same, but this will form COOH, H, the stereocenter perhaps remains the same. Okay. So, what we would expect during metabolism of this drug is some of these products. So, the next question is, given below is the structure of ceftoxamine, which is an antibiotic. The pKa of the most acidic functional group is 3.4. Okay. Question is, predict whether this drug will be absorbed in the stomach or in the intestine. So, we already looked at the pH of stomach to be 1 and the pH of the intestine to be around 6. Okay. So, the pKa of this molecule is 3.4, and we would expect that this carboxylic acid would be the most acidic functional group, and therefore, or the pKa of this functional group would be 3.4. Okay. Now, let us go through the same calculation. So, pH of the stomach equals pKa of the drug plus log of ionized by unionized, right. So, this is the same drill that we have done earlier. So, I am going to skip some steps so that we do not have to repeat the whole thing, but you can do 1 equals 3.4 plus this number. And so, if you take log of the ionized divided by unionized, right. So, this will be minus 2.4, which is going to give you, and if you take the antilog of this number, you are going to get 0.00398. Okay. So, this would be the concentration of ionized divided by unionized, that means R COO minus divided by R COOH. Okay. So, this number being extremely small, you can imagine that predominantly the molecule is going to be in the unionized form. So, we have already seen that once the molecule is in the unionized form, it can get across membranes better, and so one would predict that in this pH the molecule is going to be absorbed quite well. If you repeat the same calculation for the intestine, you will get 6 equals 3.4 plus this log of value, and so the log value would be ionized divided by unionized would be 6 minus 3.4, which would be 2.6. Okay. So, 2.6 being a positive number, what you would expect is that this is going to be a very large positive value, which means that in the pH of 6, it is going to be in the carboxylate form, that is perhaps going to be detrimental for it to be absorbed. Predict whether it is going to be absorbed in the stomach or in the intestine. Based on these calculations, we would predict that it would be absorbed in the stomach. The next question is, suggest the metabolites for atomoxetine. Okay. So, this is the molecule over here, and here is the structure of this molecule, and again we would be able to suggest that some of the functional groups that can be playing a role here is the amine. So, the amine can undergo oxidation, right, and we have already seen that the benzene rings can undergo oxidation, right, and we have also looked at the toluene position, which is going to be susceptible to oxidation, and ethers have been shown to be dealkylated under these conditions. So, this is also a possibility. So, this is dealkylation, which means that it is going to form a phenol on one side, and you could also have a situation where this NHMe is going to be an important functional group. So, let us draw out this NHMe separately. So, NHMe can undergo dealkylation. So, the methyl group can be removed. You could also have oxidation. So, you will have N oxides being formed, right, or it is going to get further oxidized. Then you could have conjugation, that could occur, and lastly you could also have methylation. Okay. So, amines are really important functional groups in many drugs, but there are a number of metabolic transformations that could occur, and so it is sometimes difficult to predict which one is going to have preference over the other. So, the major metabolites that we would look at are the toluene ring being oxidized. So, you will get CH2OH, and this is going to happen perhaps very easily, NHMe, and this can get further oxidized to give you the carboxylic acid eventually. You could also have the benzene ring undergoing oxidation by monooxygenases to give you the corresponding phenol, and as we have already looked, it is going to go to the para position. And you can also have this NHMe being further metabolized, and you could also have oxidation followed by the formation of aldehyde, which can then further undergo oxidation to give you the carboxylic acid. So, you will have this group undergoing oxidation followed by you will form the aldehyde, which can then undergo further oxidation to give you the carboxylic acid. So, these are some of the major metabolites that we would expect with this drug. The pKa of histamine is 5.74. What is the ratio of ionized to unionized histamine at pH 5.74 and at pH 7.4? Okay. So, way to address this question is to look at the Henderson-Hasselbalch equation, which is pH equals pKa plus concentration log of concentration of R in H2 divided by R in H3 plus. Okay. So, if pH equals pKa, then you get 5.74 equals 5.74 plus log of R in H2 divided by R in H3 plus. So, this term can be cancelled. So, this value equals 0, and when this value equals 0, the concentration of R in H2 equals concentration of R in H3 plus, which means that it is 50% ionized. For the same situation in pH 7.4, so you get 7.4 equals 5.74 plus log of concentration of R in H2 divided by concentration of R in H3 plus. And so, if you take the 5.74 that side, this term becomes 7.4 minus 5.74, this value is 1.66 equals log of R in H2 divided by R in H3 plus. So, if you take the anti-log of this number, you get the concentration of R in H2 divided by concentration of R in H3 plus equals 45.71. Okay. So, from this number, what we would conclude is that you have 1 divided by 46.71 is the ratio of R in H2 divided by R in H3 plus. So, 1 divided by 46.71 is nothing but 0.0214. This translates to 2.14%. So, at pH 7.4, we would expect that 2.14% of this molecule would be in the unionized form. The next question is suggest metabolites for omeprazole. Okay. So, omeprazole has the following structure as shown here, and again we could have a number of things that would happen to this molecule. So, now let us look at this in a little bit more detail, but what we would expect is that it has a OMe group. So, OMe can undergo demethylation, right, and you have this methyl group here which can undergo oxidation. This methyl group here which is identical can also undergo oxidation. The S double bond O can undergo oxidation or reduction depending on the situation, and the benzene ring and the pyridine ring can be oxidized. The pyridine ring can, of course, because it has a free nitrogen over here or a nitrogen heteroatom here, can do a number of things. It can undergo oxidation, it can undergo methylation, and we have already looked at that methylation of pyridine ring can substantially increase the polarity, and it can also undergo conjugation. So, these are the major aspects of what a pyridine ring can do. And so, with this in mind, let us look at the metabolites for omeprazole. So, we would have this CH3 undergoing oxidation to form CH2OH. You have the formation of N oxide which is possible, and this CH2OH can further undergo oxidation to form a carboxylic acid, and you have the demethylation of the OMe to give you OH. And one of the metabolites that actually is formed is shown here, which is the one with the CH2OH. Next question is, for the drug natamycin shown below, two pKa values were determined and they are 4.6 and 8.4. What are these functional groups is the question. So, let us look at this molecule in a little bit of detail. So, you have a number of functional groups here. Let us look at them one by one. You have an epoxide, you have an OH. So, epoxide does not have any ionizable or this lone pair is not going to be a very good base. You have the hydroxyl group whose pKa is well into the 14, 15 range. Similarly, this OH is going to be, all these hydroxyl groups are going to be similar, okay. And I do not see any other way, any other functional group here which is going to have a pKa less than 10. Now, you have a carboxylic acid and carboxylic acids, as we know, have pKa in the range of 4 to 6, and so this could be the one with the pKa of 4.6, and the amine here, that is the protonated amine, is going to be a good acid, and so the protonated amine, the pKa is going to be 8.4. Okay. So, the next question is, predict the ionization at pH 6.2. So, for the carboxylic acid, we will use the pKa of 4.6, and for the and the pH is 6.2. So, we use Henderson-Hasselbalch equation. So, 6.2 equals 4.6 plus log of the base form divided by the acid form. Okay. So, if you look at this value turns out to become 1.6, and then if I take the antilog after this, the concentration of base form by acid form would be the antilog of 1.6, which turns out to be 39.8. Okay. So, in order to calculate the percent value, what we would do is we would take the total amount would be 39.8 plus 1, that is equal to 40.8, and so the percent of the base form would be 39.8 divided by 40.8 times 100, which is equal to 97.5%. For the primary amine, the pKa is for 8.4, and using the Henderson-Hasselbalch equation, we get the following equation: 6.2 equals 8.4 plus log of base form divided by acid form. Okay. So, now if you look at this number, you get the value of 6.2 minus 8.4, which is basically minus 2.2, that is nothing but the log of base divided by acid. Okay. And so, if we take the antilog of this number, you get the concentration of base by acid to be 0.0063. Okay. So, now if you want to calculate the percent, then you do 0.0063 divided by 1.0063, which is nothing but 0.6%. The next question is, do all phase 2 metabolism reactions result in increased polarity or water solubility? So, as we have frequently discussed this in the previous lectures, phase 1 and phase 2 metabolism, the common theme is that there is going to be increased polarity. So, you have oxidation reactions wherein a benzene ring becomes a phenol, you have oxidation reactions where a methyl group becomes an alcohol. You also have further oxidation reactions where it can form a carboxylic acid. And in phase 2, we have looked at conjugation with glutathione, which is going to make it more polar. There's conjugation with glucuronic acid, which is again going to make it more polar, and so on and so forth. So, all these are going to increase the polarity, but not all phase 2 metabolism reactions increase in polarity. So, the example that we looked at is methylation. Okay. So, when you have an amine such as R2NH, then there are methyl transferases which then convert this to R2NMe. Okay. So, this reaction actually decreases the polarity, because previously you had the possibility of NH being polar, whereas here you have substituted the hydrogen with methyl and you are decreasing the polarity. And we have already looked at that this is mediated by this molecule called as SAM, which is S-adenosyl methionine. The other possibility is thiols undergoing the same reaction to give you RSMe, which is basically a thioether. Okay. And thioether is significantly less polar compared to a thiol. Lastly, you also have the same transformation that could occur with alcohols, and it will form an ether, methyl ether, which is going to again increase the polarity. So, the answer is not all reactions in phase 1 and phase 2 are going to increase the polarity. The next question, we are going to deal with this drug called as ranitidine. So, the most basic functional group present within the structure of ranitidine has a pK of 8.2. Question is, identify this functional group. Okay. So, in order to let us look at this molecule, this exists in two stereoisomers, which is Z and E. Okay. So, that is not going to perhaps play a huge role in the pKa values, but you have three amine centers, which we will circle over here, and if all other things are equal, then these two amines would have very similar pKa values, and they should be comparable to the other amine. But since we have an electron withdrawing group attached to this amine, the lone pair on the nitrogen becomes significantly less available. So, if we were to draw this structure in the following manner, you can draw a resonance form wherein this is going to go here and you have N double bond N O minus plus, okay, the rest of the molecule being the same. So, therefore, the lone pair is not really available for it to be donated. So, we would predict that this nitrogen would have the pKa of 8.2. The next question is, calculate the pH that is necessary for this functional group to be 10% ionized, 50% ionized, 90% ionized and 95% ionized. Okay. So, again we need to look at pH equals pKa plus log of base by acid. So, we will use this as the basis for our calculations. So, in order to look at the 10% ionized case, the pH equals 8.2, which is the pKa of the molecule, plus log of 90 by 10. Okay. So, 10% ionized means there is going to be 90% of the unionized form or the unprotonated form, and so this value is going to become 8.2 plus log of 9, which is a value of 0.95, and that is going to give you 8.2 plus 0.95, which is going to give you 9.15. Okay. So, again this pH is not practical in our system. So, in the case of 50% ionized, so you have log of ionized by unionized equal to be this ratio is going to be 50 by 50, which is going to give you 1. Log of 1 is 0, and so the pH would be 8.2. Okay. In the next case, if you want it to be 90% ionized, then pH equals 8.2 plus log of 10 divided by 90. Okay. So, this number becomes 0.95, only thing is it has a negative number. So, 8.2 minus 0.95 will give you 7.25. So, the blood plasma level, the pH is around 7.4, and so we would expect this to be 90% ionized in the blood plasma. The last part is 95% ionized. So, the principle is the same, pH equals 8.2 plus log of 5 divided by 95, and so this would be 8.2 minus 1.27. I would suggest that you go back and do the calculation yourself, and this will give us a value of 6.93.